Hi, welcome to today's video about nanowires. This is another fascinating world, nano world. This is a picture of bacterial nanowires of the species Geobacter sulfureduscens. These nanowires are conductive. Their function is not fully understood. One thing is known, they are capable of electron transport in both directions, and they are correlated to the ATP production. ATP is adenosine triphosphate. That's the energy molecule in all the cells. The energy is stored in the phosphate groups. And these bacterial nanowires could be important for the communication between the bacteria. This is a picture, short movie of growing nanowires of methyl ammonium lead iodide, CH3, NH3, Bb, S3. This is a compound with a perovskite structure. The general formula is ABX3. This method is called epitaxy. That grows on a substrate. The structure of the substrate is important for the growing material. In this case, this compound is grown on a lithographically patterned graphene. And nanowires have typically a maximum diameter of 100 nanometers. This is a scanning electron microscopy picture of titanium dioxide nanowires that were made by hydrothermal synthesis. In this picture, a color was added to show the features of the surface. This is one important method to make nanowires. That's the vapor liquid solid method, VLS. This is a chemical vapor deposition method and a bottom-up method. Bottom-up means building the nanowires from smaller units, from atoms. Here you can see chemical reaction. Silicon tetrachloride plus hydrogen makes silicon and 4 hydrogen chloride. And the silicon atoms have to travel through this droplet, which is an alloy of gold and silicon. So you have a slow delivery of the silicon atoms to the surface, which is a silicon substrate. That's the optimal conditions to slowly grow a crystal with a high order. And that's the controlled growth. And these crystals are called whiskers. And again, the structure of the substrate is very important for the structure of the nanowire. This is another example. That's bismuth nanowires. They're on a graphene film, on a bulk bismuth. And this structure can be used as a photodetector and for harvesting of light. This is suspended indium antimonide nanowires between metals. You can see this is 500 nanometers. And there's a hybrid indium antimonide and lead nanowire. It is a superconductor, but it's not a high temperature superconductor because its critical temperature is 7 Kelvin. This is very interesting, that spiky networks of nickel nanowires. Each junction acts like of the network is like a real synapse. This is a neuromorphic device. You can make memristors, which is a combination of a memory and a resistor. And imagine if you could make brain cell molecules on a molecular level, and if you could use light instead of electrons, this would give you an artificial brain, which is far superior than any brains that nature has created. And this is a picture of folding ferrite. The global permanent magnet market is a 34.4 billion market in 2021. It is expected to be a 54 billion market, US dollar market in 2026. And there's a composite magnet of iron and cobalt nanowires and hexaferrite particles. With this composite magnet, you can eliminate the use of rare earth elements which are too expensive. This nanowire is made of silicon on a patterned substrate. This can be used for photovoltaics, batteries, and because of its high surface. The nanowires have a very high surface to volume ratio. The lithium ions can nicely be placed between the wires. This gives you a high power density. And these nanowires are also interesting for cancer research because they could potentially immobilize cancer cells. This is a failed test of silicon nanowires under stress. This is an atomistic simulation made with copper. And this simulation shows that circular nanowire is the one with the highest strength. The one with the lowest strength is the triangular nanowire. This is a scanning electron microscope image of a pyrene derivative nanowire. This is in blue on pyrene derivative aggregate. This is interesting for displays. At the top right, you can see the structure of the molecule pyrene. This aromatic molecule C16H10. Yeah, another example for nanowires. This is the electron micrograph of gallium nitride on silicon. This is a semiconductor nanowire that can emit ultraviolet light, and this is a potential application for nanolasers. This is very impressive. That's a gallium arsenide nanowire. You can see the bottom here, and the tip of a scanning tunneling microscope moving along the gallium arsenide nanowire, and measure the resistance profile at 4 points. This is a nanorod. This is a 300 nanometer wide gold nanorod with beads made of 400 nanometer long polystyrene. And this rod can be rotated with ultrasound to up to 150,000 rotations per minute. This is the smallest nanowire possible. That's called EMAC, extended metal atom chains. This is an example of nona-nickel, nickel 9. Here are the 9 nickel atoms. Middle. At the end, these are typically anions. This is a string complex. These kind of molecules don't aggregate. You can use organic ligands as templates. This is the smallest possible molecular wire, and it has a big potential for transistors and for switches. This is my favorite molecule. That's the Nanocar, single molecule Nanocar. It was synthesized in 2005. You can see the aromatic rings here, basic structure, and long alkyl chains that give this molecule stability. The wheels are made of fullerene C60 molecules, and these CC bonds can rotate. That's why the wheels can also rotate. This is a 3D model of the Nanocar. This is one early step towards nanobots. This is a nice scanning electron microscope image of indium arsenide nanowires in rainbow colors. And this is nanoflower art that's made of electrochemical etching of indium phosphide. And then the color was added from an image editor. And these nanoflowers are also interesting because they could be used potentially as ultracapacitors, also called ultracaps. A nice picture. And that was today's video about nanowires for more computing power. Thank you for watching. Have a nice day. Bye bye.